Hi kids, welcome to the first video of your video lecture series throughout the rest of the year. This one is on fundamental variables and units. Some of this may be familiar to you from previous classes, but it's kind of the foundation of everything that we're going to do, so really important. Thanks for checking it out. The first thing I wanted to mention briefly is that we'll encounter two different types of numbers over the course of the year, constants versus variables. Constants are numbers that have a single value. They never change. They don't depend on anything else. And variables are numbers that have values that may change over time. They depend on other variables in the world. All numbers that you ever write in this class, whether it's a constant or a variable, should have units, which are the thing that follows the value that tells people what the physical object is that they represent. So for example, if you were going to say I have a dozen, you'd want to say what you have a dozen of. A dozen eggs is very different than a dozen piles of dog poop, for example. So the eggs or the dog poop is the unit and the dozen is the constant. Some other constants you might use: a cup. The speed of light in a vacuum is a constant, but you'd want to give the unit, so meters per second or miles per hour or something else that tells me what unit we're talking about. The number of atoms in a gram of iron. Some variables that you might be familiar with: your height is a variable. It depends on lots of things. It changes over time. The amount of money you have in your pocket. The speed of a car is a variable because it's not constant, and time itself is a variable. So I'm sure when you signed up for physics class, you were expecting a whole lot of different variables and a whole lot of different equations. I think you guys are going to be pleasantly surprised when you find out how few variables there actually are. In fact, there are only 6 variables that are known as the fundamental variables in physics. That means everything else that we come up with over the course of the year is just made up of different combinations of these different variables. And actually 6 is what they used to think there were. Now we actually, since Einstein, know there's really only 5, because 2 of those variables are actually made up of the same fundamental fabric. Occasionally throughout these lectures you'll see that little asterisk after things. I put that in when I'm actually lying to you guys a little bit. I put that in when there's more to the story than I really want to go into right now. Of course, this is your first year of physics, and hopefully you guys will go on to take many more years of physics. But your understanding should grow with you. We don't give you the whole story right at the beginning, or it would be a little bit overwhelming and confusing. So sometimes I'll explain what the asterisk is. Other times you may be interested and want to ask me about it. So if you want to know more about why there are not actually 6 variables, there's actually only 5, come talk to me sometime. So time, distance, mass, charge, color, and spin are those 6 variables. Some of those I'm sure you've seen before: time, distance, mass, maybe charge. Color and spin don't mean what you think they do. They're actually very variables that pertain to very tiny objects known as quarks. So they're not actually the physical color that you'd see when you look at something. But I wanted to make you aware that they were there. So even though there are 6 fundamental variables in physics, as mentioned before, we're actually only going to be working with 4 of them this year, but it is really important that you come up with a pretty good internal understanding of what those 4 variables mean. So the question I would start with is, what is time? If I ask that, most people will tell me something like, oh, it's how long something takes. And that's a pretty good place to start, actually. You all have been dealing with time your entire lives, and so you know what time really means internally. If I followed that by asking you what a common unit for time is, people probably tell me something like minutes or hours or centuries. And those are all good units of time. You can use any of those in this class. There is, however, one standard unit of time that physicists use when we are doing equations and calculations, and that is the second. So a follow-up question to what is time: what is a second? That's actually a trickier question to answer. Most people will define seconds in terms of minutes and hours, which presents a problem in itself, but also there's a challenge in that minutes and seconds and hours are not constant either. It turns out our Earth is actually moving further away from the sun as we speak, so today is a slight bit longer than yesterday was, and tomorrow will be even longer. There is an accurate, precise way of measuring time of seconds, and that is to count the jiggles of a tiny little atom called cesium-133, which jiggles 9 billion times a second. But for our purposes, of course, saying 1/1000 to 1000 is probably a little bit more reasonable. So the second fundamental variable we'll be using all the time is distance, otherwise known as displacement. You may have heard those terms before in other science classes. They are actually slightly different in their meanings, but for our purposes, we'll be using them interchangeably in this class. Distance, of course, is how far apart two objects are. There are many typical distance units that you've used before. An inch, which is about the length of the bottom part of your thumb. A mile, you use that to measure probably the distance to your house. Centimeter, you may have heard in science class before. In this class, we're going to be using the official physics unit, which is the meter. Just like time, scientists had a really hard time figuring out what a meter actually was. The problem is that everyday objects, like a meter stick, actually change their length all the time. Little pieces of dust stick to them, and little pieces of the meter stick will kind of degrade and fall off. So we ended up defining the meter in terms of how far light travels in a very, very short amount of time. As I mentioned earlier, light speed is actually a constant. So if you could chop a tiny, tiny, tiny short piece of light, it would be a meter long. We're not doing that in this class, of course, but I like to use the length of my leg as a meter. It's about 1 meter exactly, and I'm 5'8". So maybe just look around your house, try to figure out what feels like it's going to be about a meter for you, because it's useful to have a sense of that distance. The third fundamental variable that we'll be dealing with in this class is mass. Now, mass is defined as how much stuff an object is made up of. This is tricky because it's not the same as weight. You may want to use those interchangeably. We cannot in this class. Weight is how hard something is being pulled downwards. Mass is how much stuff is in it, right? You can be weightless. You can go to outer space and not be being pulled down to Earth at all. So you have no weight at all, but you're still made up of the same amount of stuff. So mass and weight are different, and that means they actually should have different units, and we're going to use them in different equations. So please try not to use those two terms interchangeably. Some typical units of mass: grams, tons are units of mass. Pounds is actually a weight because it's how hard Earth is pulling you down, but it is something we will occasionally refer to because you guys are so much more familiar with pounds than you are with grams. The official physics unit is a kilogram. Kilogram is about the same as the mass of a pineapple. So if you can picture yourself picking up a pineapple at the grocery store, that is about 1 kilogram. In terms of pounds, it's 2.2 pounds. So you could actually convert back and forth between them and figure out how many pineapples you are. If you've poked through your notebook yet, you may have noticed that there is a reference page that has the variables we'll be using over the course of the year, and you should see time, distance, and mass in there. Every variable that we define in this class will have a symbol, so it's just a shortcut way of writing time without writing the whole word out, because physicists are lazy. So for time, it's a T. For distance, it's a D. For mass, it's an M. Those are nice, intuitive ones, but they might get a little trickier as the year goes on. A short description, and then the typical unit that we're going to be using in this class. Every lecture will end with a short summary, which is the takeaway points that I want to make sure that everybody gets. In this case, you should be able to figure out the variable, the symbol, and the unit for every number that you encounter in this class. The variable is going to be important because we want to have a common language that other scientists and your teacher and your peers can understand. The symbol that you use is just a nice shortcut, and we'll be using those in equations. And the unit takes a plain old number and turns it into a real object. It also tells you roughly how big or small it is. So 6 miles, we know it's a distance because miles is the unit, and we know it's a pretty big distance because miles is a pretty big unit. If you are a student that is nervous about knowing these things, it is sometimes beneficial to make a flashcard. You can use that reference page in your notebook to make flashcards for the different variables and units and practice on those. All right, thanks for listening.